Welcome back, everyone. Welcome to another lecture in our series on non-smooth optimization theory. So today we are diving into a theorem that actually forms the bedrock of convex minimization problems. After all the groundwork we have laid in previous lectures, right, that I strongly invite you to check out, we are now about to uncover a key result that shed light on the existence and uniqueness of solutions of convex minimization problems. So you may probably wonder why this matter, right? Especially in the context of cutting-edge technologies like artificial intelligence. Well, imagine you are training a machine learning model, right? I mean, say for image recognition or whatever, right? So the goal is usually to find the best set of parameters that make your model not just good enough, but exceptional at identifying objects in images. And the process often involves optimization, right, where you want to minimize a certain error or loss function. But the catch is that the space of possible parameters is actually vast, right? And blindly searching through it would take forever. So you need an alternative way of kind of characterizing minimizers of your functional, right? Or the function you want to minimize. I strongly invite you actually to watch my video on the Fermat principle. I'll put the link at the upper right corner of the screen, which basically gives us an alternative way of characterizing minimizers of functionals that are at least Gato differentiable, right? So please check it out. So however, the theorem we are exploring today, help us understand when our optimization process guarantees a solution, right? And better yet, when that solution is unique. In the realm of machine learning, where every fraction of improvement matters, having a theorem that guides us, I would say, towards certainty and efficiency is definitely a game changer. So let's take this theorem per se, right? This will be theorem 3.7. So let X be a reflexive space a reflexive Banach space. Right, and let's call it 1. So let U, right, be a subset of X, right, be non-empty, convex and close, convex and close. Second point is that so let F, right, be a function defined on U into the 2-point compactification, of R bar. So let F be proper, convex, and lower semi-continuous. Right? I'll just write LSC for lower semi-continuous, right? So with domain of F, right, intersected with U different from the empty set, right? So the domain of F should intersect the set U. Okay, and finally, we need a third assumption. Our third assumption is that either U is bounded, right, or F is coercive. So if those three conditions here are actually are met, right, then the problem of minimizing the function f of x, right, over x in u, right, that meets the solution, right? And well, let's can even characterize, that means the solution x bar, right, solution x bar that lies into the intersection of u and the domain of f, right? And furthermore, if our function f is strictly convex, then the minimizer is unique. If f is strictly convex, the solution is unique. Okay, so let me just highlight some important fact. So our space X should be reflexive, right? This is an important property, right? Because I mean, you can already think of I mean, a Belain-Schmidlen theorem, right? Because we know that if you have a bounded a bounded subset of a reflexive space, then there exists a a weakly convergent subsequence, right? And then the candidate of that that subsequence is usually the minimizer, the candidate for the minimizer. Okay, so let me also highlight strict convexity, right? It is actually very important for uniqueness. I mean, without strict convexity, you cannot hope for uniqueness of your minimizer, right? So this is actually due to the fact that you can basically have let's say you have something like this. So let me just say you have well, you can actually have how would I draw it? You can have something like a valley, right? You can have a function f like this, capital F like this, right? This function f of just say is convex, right? Because the epigraph of the function f here is actually is convex, but and also has minimizer, but the minimizer is not unique, right? Because every point lying here, right? It's a minimizer of the function f. So here, you have a function that is convex, you have the existence of the minimizer, but the minimizer is not unique. And this is due to the fact that the function f here is not, this function here is not strictly convex, right? So strict convexity is actually, is needed for uniqueness. Okay, so let's go into the proof. So for the proof, observe first that, so note, first thing you need to observe is that minimizing the function f of x, right, over x in u is equivalent to minimizing the function f of x, right, plus delta u of x, right, over x in x, right? If you don't remember, this, I wanted to change the color. Yeah, the indicator function was actually defined to be 0, right, if x is in u, right, and plus infinity else. Okay, so this is, this equality is actually easy to see, right? So now, because of this observation here, we consider the, call it the extended functional, let's call it f bar, right, defined by f plus delta u, right? This is the function defined from x into r bar, right? So this means, what it means is that f bar of x is actually f of x plus the indicator function of u at the point x, right? And this of course holds for every x, right? So let me just write it over here. This is for every x in x. Okay, so in order to prove, our goal basically is actually to, our goal is basically to apply the direct method of calculus operation, right? To get the existence of the minimizer. Apply the direct method of calculus operation, right? So so we probably use different color. So this means that we need to check that, we need, just for your recall, if you don't remember the assumption of the direct method of calculus operation, so we need to check that our extended functional f bar is proper, right? Cohesive and weakly lower semi-continuous. Okay, so those are, we need, if we are able to prove that our extended functional f bar is proper, cohesive, and weakly lower semi-continuous, then we can basically conclude about the existence of the minimizer of our functional f bar, and therefore of our functional f. Okay, so so let's start. So assumption, our first assumption, so assumption 1, just highlight it. So, assumption 1, so this is U is non-empty, right? Convex and closed. Implies that, so this assumption implies that the indicator function delta u, right, is proper. Properness follows from the fact that u is non-empty, right? Delta u is also convex, right? Because u is convex. And weakly lower semi-continuous, right? This is due to the fact that so just the weak lower semi-continuity follows from the fact that U is convex and closed, right? Convex and closed, right? If you check out my video on the direct method, I actually prove it, right, in that video. Okay, so our delta U is proper, convex, and weakly lower semi-continuous. And now from assumption 2, right? From our second assumption, we obtain from the fact that, the domain of f, right, intersected with U is non-empty. So we obtain from this condition, from this assumption, that there exists, right, a point x0, right, in U, such that f bar of x0, right, is equal to f of x0, right, which is which is finite, right? Because x0 is actually in the domain of f, right? So, and hence this proof that f bar is proper, right? Because I mean we have an element in the intersection, right, in the domain of f bar, such that f bar of x, f bar of x0 is actually finite, so the domain of f bar is actually is non-empty, right, and therefore f bar is proper. F bar is also convex and weakly global semi-continuous, right? This follows from the fact that this is a sum of two functions that are proper, convex, and weakly global semi-continuous. Okay, so so you have already that f bar is proper, convex, and weakly global semi-continuous. So it remains to prove that f bar is coercive, right? So finally, f bar is coercive. Indeed, this is due to the fact that indeed from the third assumption, this is the assumption that we haven't used so far. From assumption 3, so from assumption 3, right, remember assumption 3 actually says that either U is bounded, right, or F is coercive, right? So for U bounded, we can actually, we can use, we can use that, F is actually greater than minus infinity, right, to conclude. I will tell you why. To conclude that f bar is actually is coercive. Well, this is because let me just use another column. In fact, if you have, as the norm of x actually goes to plus infinity, we know that x is not in U, right? Since U is bounded. U bounded means that the norm of x cannot go to to plus infinity, right? So if you have norm of x going to plus infinity, then x is actually not in U, right? Since U is bounded. So this means that by definition of the indicator function, delta U of x is actually equal to plus infinity, right? However, as our functional f is actually greater than minus infinity, right? You have that f bar of x, right, which is equal to f of x plus delta U of x, right, is, this obviously goes to plus infinity, right? So, okay, so if U is bounded, then our extended functional f bar is coercive, right? So, now in the other case, right, however, for f coercive, right, we we can use that. In this case, it's even easy, right? It's even easier. We can use that delta U is actually greater or equal than 0, right? To conclude that f bar is coercive, right? In fact, you have f bar of x, right? By definition, it's actually equal to f of x, right, plus delta U of x, right? But of course, this delta u of x is actually greater or equal than 0, right? This is by definition. So therefore, f bar of x is actually greater or equal than f of x. Now remember, this, f bar cohesive, right, implies that, or functional, f cohesive implies that f bar is cohesive. Okay, so basically, all the requirements, right, for the direct method of calculus of variations are satisfied. So hence, we can basically conclude, we can apply the direct method of calculus of variation. I just write COV, right, for calculus of variations. It's a shortcut to obtain the existence of a minimizer x bar in the domain of our extended functional f bar. But this domain of f bar is nothing else than u intersected with the domain of f, right? It should be the domain of delta u, right, intersected with the domain of f, but the domain of our indicator function is actually u, right? So let me just highlight before we move to direct method of calculus of variation. Okay, so this is with f of x bar, right, is equal to f bar of x bar, right? This equality here follows from the fact that delta u of x bar is equal to 0, right? So, and this is less or equal than f bar of x, right, for every x in u. Okay, so this means that x bar, is actually the claimed solution. Okay, so this is about existence. Now let's go to uniqueness, right? So uniqueness. So for uniqueness, we actually saw that we need strict convexity. So let now f be strictly convex. And let x bar and x bar prime, right, be in U, right? X bar and x bar prime are actually say there are two different solutions, right? Oops, two different minimizers of our functional f. So this means that f of x bar is equal to f of x bar prime, which is exactly the minimum of f of x, right, over x in U. And of course we said that they are different, right? So okay, so then for such x bar and x bar prime, it follows from the convexity of the function f that then by convexity of, first of all, of the set U, we have that 1 over 2, right? I mean, use a convex combination of the two elements is still in U, right? So 1 over 2 x bar plus 1 over 2 x bar prime is in U, right? Now if you use the strict convexity of the function f, so while the strict convexity of f, right, implies that f of 1 over 2 x bar, right, plus 1 over 2 x bar prime, right, is actually strictly less than 1 over 2 f of x bar, right, plus 1 over 2 f of x bar prime, right? But I mean, by definition, this is exactly equal to the mean of f of x, right, over x in U, right? And well, this is again f of x bar, right? But this is actually a contradiction, right? So, but this is a contradiction to the fact that f of x bar is actually slightly less than f of x, right? For every, I mean, or say that's equal, right? For every x in U, right? So this is actually the end of, I mean, of the proof of the theorem. Okay, so I think now you are well equipped, right, with tools actually to actually I mean to say when the solution of an optimization problem actually exists and when it is unique. Okay, so let's have a remark, I mean a couple of remarks. So remark, so for the sum of two convex functional to be cohesive, right? So for the sum of two convex functionals to be cohesive, it is in general not enough it's in general not enough that only one of them is cohesive. Right? I mean, functionals for which this is the case, I mean, are called super cohesive, right? So let me just write it here. So functionals for which this is the case are called, put it in color, probably this color, are called super cohesive. Okay, I mean, an example that, I mean, which will be super helpful later in this lecture series is actually the square norm, right? And this result is actually encapsulated in the following lemma. So this is lemma 3.8. So let f, right, defined from x into r bar, right, be proper, convex, and say and lower semi-continuous, right? Obviously lower semi-continuous if you want. And lower semi-continuous. Let's see. So let me just highlight properness, convexity, and lower semi-continuity. And say you have a point x0, right? That lies in x, right? Be given. Then the functional j, right? Defined from x into r bar, right? Which maps x to to g of x equal to f of x plus 1 over 2 norm of x minus x0 squared. Oops. Then this functional is actually cohesive. Okay, so we're not going to prove this result, right? I'm just going to give you, an idea of how you can go about the proof. It's actually not difficult, right? So to show that this functional here, this functional j is cohesive, so the idea would be to lower bound j by a cohesive functional, right? So lower bound j by a cohesive functional, right? And this is actually possible due to the fact that so the way to go is actually as follow, right? As your functional f is proper, right? As f is proper, convex and lower semi-continuous, right? We actually know that f actually coincide with its convex envelope, right? So f equals to f gamma, right? We denoted by f gamma the convex envelope of f, right? So this means that f is lower bounded by an affine functional, right? And this actually follows from the definition of the convex hull, right? Convex envelope of a functional f. So this means that we have something like f of x actually greater or equal than x star comma x, right? This is actually the duality pairing, right? Minus alpha for some. This is for some alpha in R, and of course for some x star, for linear bounded operator x star. And now what we have to do will be just to use the reverse triangle inequality. So say use the reverse triangle inequality, right? And also the fact that the absolute value of this duality pairing here, and this is by definition, right? This is actually less or equal than the operator norm of x star, right? Times the norm of x in x. Okay, so this will be enough for you to to conclude, right? So it's not a big deal anyway. Okay, so before closing this lecture, I would like at least to state the following remarkable result, right? Even if you're not going to prove it, but I think this is really important for you to know. This is theorem 3.12. So let X be a Banach space. if you have a functional f, right, defined from x into r bar, right? So if f is convex, and just use the same color. F is convex and lower semi-continuous, then let me just highlight convex and before you proceed. It's convex and lower semi-continuous, then f is locally Lipschitz continuous, and f is locally Lipschitz. This is C missing. Lipschitz continuous on its domain, right, on domain of f. So if you have a Banach space X, right, and you have a function f, right, defined on the Banach space X into R bar that is convex and lower semi-continuous, then f is locally Lipschitz continuous, right, on the domain of f. So we cannot actually hope for, a global Lipschitz continuity, right, because we are actually dealing with an extended, we are dealing with an extended, let me just highlight it here. So we are dealing with an extended real valued proper functional, right? So there is a point of discontinuity somewhere. There is a jump at some point, right? So you cannot actually hope for a global Lipschitz continuity. So this is actually an amazing theorem, right? As it actually illustrates the beauty of convex analysis, right? Because here we have an algebraic, an algebraic property, right? Notably convexity that connects two topological properties, notably neighborhood and continuity, right? This is actually, it is really a striking feature, right? And I also get reminded of the Millman-Pettis theorem, right? Where we have that, a geometric property actually implies a topological property, right? When we actually talk about the Millman-Pettis theorem, we actually saw that, a uniformly convex space is actually reflexive, right? Yeah, if I remember. So yeah, well, so this is actually a very nice and really striking feature, right? So for the proof, so let's go into the proof. By the way, if you're interested into, if you're interested in functional analysis, I strongly recommend you checking out my my playlist, right, on functional analysis, right? It's really nice and yeah, well explained. Okay, so for the proof idea, right, we are not going to the whole proof, right? Just give you an idea of the proof. So for the proof, the first step for you would be, the step one. So the first step for you would be to show that that bounded convex functionals are Lipschitz continuous, right? So first thing is show that bounded convex functions are Lipschitz, right? And the second step would be for you to show that, we use a different color. So in the second step, you will prove that convexity plus lower semi-continuity, right? Plus lower semi-continuity, that these two properties implies that your function is locally bounded, right? Right. So yeah, if you do this, then you are you are done. Right? Because remember, in assumption, we have a function that is convex and lower semi-continuous, right? So if you prove that convexity plus lower semicontinuity implies that the function is locally bounded, then you can now come to step 1, right, where you actually prove that any bounded and convex function is actually Lipschitz continuous. So you are basically done. Okay, so with this we wrap up today's lecture, right? So stay curious, stay inspired, and keep pushing those boundaries. Until next time, happy learning. Yeah.